Let's talk about how inorganic complexes bond. And in order to do this, we can talk about something called crystal field theory. Now, I have sketched out, perhaps poorly, the shapes of the d orbitals. So let's walk through these so that we can see what we're going to be bonding with. Because d orbitals for transition metal elements are the valence shell, and that's where a lot of the bonding is going to take place and a lot of the interactions and consequently some of the properties of them. So, if you recall, dz squared has two lobes and this kind of donut in the middle of it, and those lobes are in line with the z-axis. That's going to be important. X squared minus y squared, that particular d orbital, has four lobes, like a four-leaf clover, and they are centered on the x and y coordinate axes. Now, the rest of them, xy, xz, and yz, are all in between the coordinate axes. So it's this first one right here, xy, it's very similar to the x squared minus y squared, except just rotated just a few degrees, about 45 degrees, so that instead of being in line or centered on the coordinate axes, they're now in between the coordinate axis. And then a very similar layout for xz. It's in between the coordinate axes, but lined up in the xz plane, which happens to be the paper's plane. And in this case, we have yz. So it's in this plane, kind of the perpendicular plane to the paper. And again, in between the coordinate axes. Well, why is it important that I'm mentioning in between the coordinate axes or directly on the coordinate axes? Well, that has to do with where our ligands sit. So let's draw some complex. So we have this, and we have some metal, and then we have ligands, right? And each one of these ligands in an octahedron is directly in line with the coordinate axes, right? So, and how do ligands bond to the metal? Well, generally they're going to have a lone pair of electrons, and those electrons are going to be donated to the metal, right? That's going to form our bond. So we have electron density at this ligand that is being fed into the metal. Well, there's two orbitals, the z squared and the x squared minus y squared, that are going to get in the way. Those are going to have electron density pushed into these orbitals. Right? So what that will do is split the d orbitals into two groups. This group and that one. And this one will have a lower energy because these ligands are not directly interacting with these orbitals. They're not feeding electron density in. See, normally interacting with an orbital would be a good thing and it would lower the energy. But it's not a good thing if we're feeding in two electrons into that orbital. That will fill it up. So that will increase the energy of these two orbitals, and these orbitals will not have as much increase. So what will that do to the d orbitals? Instead of them being all at the same energy level, there's 5 orbitals at the same energy level, this is what would happen if we had no ligands on the metal. But once we do, 2 of them will shift to a higher energy level, and 3 will shift maybe a little lower, or perhaps just a little bit higher energy level themselves, but significantly lower than these two right here. So something like this. And we'll just say this is z squared. This is x squared minus y squared. xy, xz, and yz. So they split into these two groups. Now, if you use symmetry to explain the bonding in octahedral environment, there is a whole group or a whole way to name things in there. And I'm not expecting general chemistry students to know what those are, but or really do much with it. But these are called the T2G orbitals, and these are called the EG orbitals. T stands for triply degenerate, so there's three orbitals here, so three orbitals at the same energy. And then the other part is let's see here, 2. That's an anti-symmetry about, I believe, some kind of either rotation or something. It depends on what point group it is. And G is just, it's symmetric about inversion. So if I flipped one side of this to the other, it would be symmetrical. And all of the d orbitals are symmetrical, and so that's why both of these are Garrod, or symmetric about inversion. And E is doubly degenerate, so it has two orbitals. Now, what can happen is the difference between this splitting can change, and that will depend on the ligand. So if I have a ligand that's really strong, then very well at donating electron density into the metal, this can split further. And if I have one that's weaker, then these energy levels will be closer to each other.